did a chapter about circular motion, so things that moved in a circular path, but not things that rotated. And there's a difference between those two things, right? I can walk in a circular path, or I can spin. Okay, so those two things make a little bit of a difference. So we're talking about things that are spinning. Okay. So I know this is long, but I want you to put down that definition for angular displacement. I want you to think about what it means as you write it down. Okay, don't just mindlessly copy down words. Okay, think about what's happening. And then I'm going to talk through here just a little bit. So as you're putting this down, I want you to think, I think there's two things in this passage or this definition that might be questionable to you. Okay, or you might not understand why that is the case. Okay, so look through that definition and see if there's anything in there that you don't quite understand. There's at least two things that I want to point out to you in this definition. Okay. No. That's not the go-to example, like some chapters have go-to examples. Okay, does anyone have a one of our points that we might have questions about here? Or do you see anything that you have a question as to why? Yeah, Cece. That's right. Counterclockwise. She's asking, why is counterclockwise not negative, right? It says counterclockwise, it is positive if it is counterclockwise, and negative if it is clockwise. So why is that the case, right? That seems counterintuitive to us. If we look at this object from above, okay, so I'm looking at it from above. Here's our object. These are our axes. Okay, where's the positive x-axis? Right, here's our positive axis. And which quadrants of our coordinate plane here are positive? The top two, right? And the bottom two are the negative quadrants. Isn't that right? So if we assume it starts at the positive horizontal axis and moves in the counterclockwise direction, it's moving in the positive direction. Okay, that's why they're saying counterclockwise is positive. Right? If you look at the coordinate system and it moves counterclockwise, it means it's moving toward the positive direction. Okay, assuming that we start at the positive x-axis. Okay. The next thing that I want you to maybe notice, is there anyone else or anything else that we can see here? Any other questions? This one's not as obvious, I think, but it says when a rigid body rotates. Okay, so what does that mean that it has to have or have to be? Okay, maybe a better question is, what could it not be that we're looking at? We're not looking at fluids, right, or liquids or things that don't have a fixed shape, right? A rigid body is something that has a fixed shape. It's not going to have a center of mass that's moving along with our rotation. We're not going to be like rolling all over the place here. This is something that is spinning pretty uniformly. Does that make sense? So a rigid body means it's a solid particle of some kind that rotates about a fixed axis. So we're not like on the tilt-a-whirl here going up and down and spinning and doing whatever. It's just spinning. Okay, make sense? All right. So here's a couple equations that I want you to look at, and I know it's a lot here on the screen at one time. This is what I want you to look at first, this diagram of our, you guys know what this is? Yeah. Okay, eventually I'm going to teach classes that don't know what that is. But this CD, you can see this basically chunk of our circle has been cut out. Okay? A chunk of our circle has been cut out, okay? And this, what's this Greek letter called? Theta. Theta, good, that's called theta. And this is going to be basically our angular displacement, right, what we just learned about. Okay, so that whole definition that we just wrote about angular displacement is theta. That's the variable that's going to go with it. And we measure theta in radians, not in degrees. Okay, we measure theta in radians. And what theta is the chunk of the circle that's being covered as something is rotating. Okay, so if my CD is spinning in this direction, during this little time frame, it's covered this much chunk of the circle, which we would measure in radians. That would be its angular displacement, right? How far has it moved, or what portion of the circle has it covered during that time? Does that part make sense? Okay, so angular displacement. What angle has it covered of our circle during that time? Okay, that's what angular displacement means. We represent that by a theta, and it's going to be measured in radians. Okay, so this equation that I would like for you to have down, theta equals L over R. Okay, L is going to be our arc length here, and R would just be radians. Okay, so L and R should both be measured in what unit? Meters. Meters. It's a distance, so we want it in meters. Theta would then be in radians. Okay, not then. The meters are going to cancel. That doesn't really matter to us. Okay, and then hopefully this is a little bit of a review here. 360 degrees is equal to 2 pi radians, which is 1 revolution. Have you learned that hopefully in math sometime at some point? Okay, that you will need to be able to convert from radians to degrees and back. You'll need to be able to convert from revolutions to radians and back. Okay, so those are 2 conversions that you need to be able to know how to do. Okay, from radians to degrees and radians to revolutions. So 1 revolution equals 2 pi radians, 1 revolution equals 360 degrees, which means 2 pi radians equals 360 degrees. Okay, so we see how all those things mean the same thing? All right, so here's a couple other terms that we're going to look at. Angular displacement is delta theta, right? That's what we looked at first. What chunk of the circle we're being covered during a rotation. If we ask about angular position, it's almost the same thing. It's just not delta, right? We're just looking at what position it's at that exact point in time. Okay. That's rare that we would solve for angular position. Most of the time we're going to find out how far has it traveled during this certain point, which would be a displacement. Okay, would be a delta. Angular velocity is the big thing that we're going to get to today. Okay, and angular velocity is a Greek letter called omega. Okay, so you already have the definition for angular displacement. You probably don't need to put that down again. But angular velocity is what we're going to get to today. So can anyone kind of describe to me what angular velocity might mean? We know what angular displacement is. What would angular velocity have to mean then? Yeah, how fast it's going, particularly how fast it's covering the circle, right? How fast we're getting around the circle. That's what we're talking about here. How quickly are we covering that chunk of the circle? Okay? And the equation for angular velocity is omega. Okay, the computer sometimes writes it differently. I will always write it like this, right? A W with some wings on the end. Omega equals delta theta over delta t.
Probably gonna have to like solve the displacement, and just plug in over T actually.
The kinematics equations are coming back for this section, except we're going to put them with new variables. Yay! Okay, this last little bullet here means something to us. Okay, every particle in a rotating object moves with the same angular velocity. Why would that be the case? Okay, hint, it has something to do with what we explained on the first slide. It's a rigid body, right? Nothing's lagging behind. Everything's set in place. It's going to be moving at the same or rotating at the same speed. Very nice. All right. Radians per second is our unit for angular velocity, right? If we are in radians here over time, which is seconds, they should be radians per second. So this is a velocity unit, okay? Angular velocity unit. Okay, now we're going to look at angular acceleration. If we know anything about acceleration, can we predict what we think the equation for acceleration might be? Not meters per second squared. What did you say? Did you say meters?
Radians per second squared.
Radians per second. There we go. That's all right. Radians per second squared. That's alpha. Okay, again, the computer writes it a couple different ways. This is how I'll write it. Alpha. Yeah, pretty much a Jesus fish. Okay, average angular acceleration, which is what we're solved for most of the time, is measured in radians per second squared. So here is our equation here. Alpha equals delta omega over delta time. There's also a second type of acceleration that we can call radial acceleration, which is kind of a linear acceleration, right? If it was to leave the circle or to stop rotating at some point and kind of look at basically our radian change, okay, we would use this equation of omega squared times r, okay? So these are two different types of equations that we can use to solve for that angular acceleration or radial acceleration, okay? So this one is kind of adapted from our centripetal acceleration equation. So if it's moving in a circle and it's rotating, right? If it's moving in a circle, we would use this equation here. Centripetal was in chapter
AR
5.
Is it B2 B squared over R?
Yep. Okay. So radial acceleration, when we talk about centripetal acceleration and or radial acceleration, open up your book to page 212. So on page 212 on the bottom left, we see something called tangential acceleration and radial acceleration, radial or centripetal acceleration. And when we looked at circular motion, where was the acceleration always pointing?
Just like the way it came off.
That's tangent, right? Its velocity would be tangent to the curve, but it's, yeah, centripetal means center seeking. So if you see here on this picture here of our wheel, our radial acceleration is going to be toward the center. And our tangential acceleration, which is our linear acceleration, right? If it were to fly off of its circular path at that point, that's where it would be accelerating toward. Okay, so we have a couple different types of acceleration here that we're going to look at. Radial or centripetal acceleration, you would use this equation, and then I'll give you another equation if we solve for tangential acceleration. Okay. If you really, really are interested in the completely specific differences between those three things, you are more than welcome to read page 212. Okay. All right. So we're going to find a way to connect linear motion, which is moving kind of in a straight path, and this rotational motion. Okay. Linear motion is motion of the object without rotation. We can still solve for values like regular velocity in meters per second. We can still solve for distance, L, or the distance traveled, or regular acceleration. Okay, that's going to be our tangential acceleration, is our linear, right, where it would move in a straight line. Okay, and so here are those equations that do that for us. Okay. These allow us to connect a rotating object and look at it as if it were going to be moving in a straight line. Okay, so it takes that object out of rotation and moves it in a straight line, and this would give us the ability to look at what speed it would be going in meters per second rather than radians per second. Yes. Oh, wait, no, it's not. No. This is just tangential acceleration, so this is regular A. This would be measured in meters per second squared. Meters per second. Okay, this part is the alpha. Is this what you were asking? I am so sorry. Yes, you are right. Alpha and omega there. Yeah. This is regular acceleration, so when we see a regular A, that's going to be meters per second squared. If we see our alpha, okay, or our Greek letter, that would be measured in what? Radians per second squared. Okay. I understand that this is still a little bit confusing because there's 3 different types, but that's how we would look at that. And some different equations, yes. All right, so we talked about how our angular velocity of every particle within that rotating object is the same, right? It's angular velocity. It's moving at the same rate, or it's covering the same chunk of the circle no matter where it is along that path. But the difference here is that the linear velocity is different for particles that are further from the axes.
What else should we have in our equation sheet?
I would have these 3 for sure. And the one I gave you with, pretty much everyone I've given you so far should be on your equation sheet.
Nice.
Okay. This one has a lot. Okay, so as our radius changes, okay, so let's picture yourself on a merry-go-round, okay, and you're really, really on the outside of the merry-go-round, okay, so you're on the very edge. You are moving at the same angular velocity, right? You're covering the same chunk of the circle as it's moving as you would be if you were standing at the very center of the merry-go-round, okay? But the truth is, the closer you get to the center of the circle, if you were to fly off the merry-go-round at that point, you would be moving faster, okay? Although it feels a little different to us as we move inside and outside on the merry-go-round, where does it feel like you're moving faster at? On the outside, right? You're covering basically a chunk of that. You're covering the same chunk of the radian, the same chunk of the circle, but you're traveling a farther distance. Right? So it feels as though you're going faster, okay? But that's not really the case, because as your radius would increase here, what would happen to your linear velocity? If you increase this radius, right, if this was 10 divided over, or if it was 1 divided over, what would be the difference? Your velocity, okay, let's think this through. Think this through, okay? If we were trying to solve for velocity, and when we divide this over, this would become our denominator. So if our denominator right here gets larger, does our velocity increase or decrease? It decreases, right? So the farther away you get from the center of the merry-go-round, your linear velocity would decrease. Okay? All right. Linear acceleration or tangential acceleration, we just talked about that. This would be regular meters per second squared. Okay, what does frequency mean without looking at the board? All right, you already had it down. Okay, frequency is the number of revolutions you can make per 1 second. Frequency you can make per 1 second. So revolutions per second would be the unit for frequency, or we can also call it hertz. Hertz, okay? We can connect frequency and angular velocity using this equation. Okay, and then this is an old equation that we know how to connect frequency and period. Okay.
What's period again?
Can someone remind us what period means?
How long it takes to go one way.
That's right, that's right. So, that's right, seconds per revolution. Seconds per 1 revolution, so you can really just drop that 1 revolution. Seconds is the units for period, but yes, you're right.
I
Didn't get that, okay. Okay, period is the seconds it takes for one revolution.
Yeah.
Okay, so since it's going to be over one revolution, the unit for period is just seconds, right? Because it's seconds over one revolution. If it's divided by one, then it's... Okay, so the period unit is just seconds. But you are right. It's the seconds it takes per one revolution. Okay? All right. Questions here? I know we got a lot of equations today. All right, let's go. A wheel accelerates from rest to 400 RPM in 20 seconds. Calculate the angular acceleration. What do we think RPM stands for? Rotations or revolutions per minute. Does it stand for radians per minute? No. So we have to convert that. Okay, you have to do a conversion here from 400 revolutions per minute, right? Whenever we say per, that goes on the bottom of our T-chart, revolutions per minute. Okay, so when I do this conversion, I'm going to go from revolutions to radians. Okay, what's my conversion factor between revolutions and radians? Good. 2 pi radians equals 1 revolution. Okay, so I'm done with revolutions. Now I'm in radians per minute. That's not what I want. I want to go 1 minute, 60 seconds. Oh, I don't like pi. Literally and figuratively, I don't like pi. Okay, don't... You guys didn't even laugh at my joke. So please don't leave a pi symbol. Give me a real answer. Okay? So, we want angular acceleration, which is alpha. Okay, so we need delta omega over delta t. Angular velocity. That's what this is, right? Radians per second, that's angular velocity.
So that's omega.
What's our... Okay, it says it goes from rest, so it's final minus initial. So this is going to be final or initial?
That's going to be
Final, right? We did a conversion, that's 400. So when we plug this in, we would say 41.89 minus our initial, which was 0, because it was at rest, over t. Okay, so 2.09 radians per second per second. Okay, so during that time, it increased in angular velocity at a rate of 2.09 radians per second per second. Questions there? Is this coming together? Yeah.
What? Stop talking about.
.2 meters from the center. That's going to be our radius, right? Even if we're not sure that it's all the way to the end or if it's in the, we don't know, that's going to still be our radius, okay? So radius equals 1.2. What does this tell us right here? The period, good, is 4 seconds. Can we use period in any of these equations we were given?
frequency one.
Yeah, frequency. Okay, we want linear speed, so what variable does that mean we're solving for?
I don't know.
V, regular V.
Equals R omega.
Okay,
Is that right?
okay.
Is that right?
Look at some other equations that we have. I'm trying to find mine here. Okay, so here's some equations that we have. We have L, and that's not what I want. V equals R times omega. Do we have an equation to connect frequency and omega?
2 pi frequency equals omega.
Okay. 2 pi f, right? So are we going to have to connect these two equations?
It has to be 2 pi times.
Okay, but first we have to take frequency from the period, right? All I'm taking is frequency equals 1 over t. Okay, so I'm going to plug that in here. Omega equals 2 pi times 0.25.
You take that.
Okay, I got about 1.57 for my omega, or my angular velocity. Then I'm going to take my radius times that omega, or angular velocity. And I should get my linear velocity.
Which is radians per second.
Regular V is regular velocity, which is meters per second. Okay. Linear speed would be the speed that it would travel if it was ejected from the merry-go-round at that point, and it would fly off, right? If you take your little sibling and you spin them around, by their arms, and then you let them go like Matilda style, okay, and they fly off, that would be the linear speed. Okay, everyone picturing what I'm talking about there? Okay, I think it's by her hair.
Is that comfortable?
I don't know anything about computers. I took this question from somebody else. Yeah, that's all you have to do. All you have to do is convert this from RPMs to radians per second. That's it.
That's it?
That's it. Okay, and you can make up a shortcut if you want to, because it's just going to be 2 pi divided by 60, right? Times 2 pi divided by 60. Okay, that would be the shortcut. Okay, when you are converting these, you should get roughly 10% of your original value. Okay, not exactly, but roughly 10 to 11% of your original value. So what did we get for our conversion here? Did we get 565? Hopefully? Yes? Okay.
What time are you alive?
All right, go ahead and find our linear speed now. Okay, we want to find the speed of the disk at that point, 3 centimeters from the axis. We have omega.
Oh, it's 3 though.
We have our radius. Did we remember to convert from centimeters to meters?
Yeah.
Okay, 0.03 times 565, and we got about 17 meters per second. Okay, there's your homework assignment.
Oh. Ooh.